So this is lecture 3.1, and today in class we talked about a little bit about waves and a little bit about a term called wavelength and a little bit about a term called frequency. And that's what we're going to discuss about the parts of a wave right now. Okay, the concept we looked at was the concept of waves. Right, not waves in the sense of physics waves or sound waves or anything like that, but we're in light waves. And more importantly, the wave component of electrons. All right, so like I said in class, kind of take notes as I go along here. So if I have a wave here, let me just draw that wave. All right, and I'm going to label some parts that we kind of discussed in class, but I have similar points here, peaks and valleys. All right, so if I want to look at those peaks and valleys individually, I can break this wave down into similar parts. From here to here is identical, or one part, and from here to here is one part, and from here to here is one part. So I kind of split those right there. So all of these right here, this one, and that one, could be termed a wavelength. A wavelength is just a repeating pattern from one point on a wave to another point on the wave. All right, it can be taken from any point on the wave. All right, so that's the wavelength of a wave. The other term we talked about was the term frequency. So if I have a wave, and say this is a span of 1 second, all right, so I have a certain amount of wavelengths that pass within that 1 second. So here, I'll start, I'm at the bottom, let me get another color here, at the bottom of the hill right here, and I go to the bottom of another hill, that's one wavelength. And then to the bottom of another hill, that's another wavelength. So basically down here I have 2.5 frequency. I'll write it over here, frequency. All right, so let's define those terms. Okay, so a wave, or a wavelength. Okay, and it's denoted by a Greek symbol called lambda. That's that. It's kind of a line with a line coming out on it. I can draw it tomorrow a little bit better in class, but it is the distance between two repeating points on a sine wave. Two repeating points on a sine wave. Okay, so a sine wave, again, is right there. A simple sometimes they call that a sinusoidal motion. A sinusoidal motion. So if this was on an XY axis, this would be what is considered a sine wave. Just ask Tech and she'll tell you all about it. And the other term we looked at is the term frequency. Frequency, and it's denoted by kind of a Greek symbol there. It kind of looks like a V, but that is the number of waves. Oh gosh, I can't write. I'm going to have to get used to this. That pass a fixed point in exactly 1 second. In 1 second. All right. Now these have some special units. All right. We usually measure this in cycles per second. Okay, so 1 over seconds. So we call, like, for instance, you can that wave, a peak of a wave passed there 5 times within 1 second. So that'd be a cycle per second. So 5 cycles per second. That is also equal to seconds minus 1, because seconds is on the bottom here. I can represent that as seconds minus 1. We also have a term called hertz, which is denoted Hz. So hertz is another measure of frequency. And over here, up here, distance is measured in meters. All right, so I have all my terms there. Now, some of these terms go with a few equations. Now, we're going to do an example with each type of these equations. Okay, the first example takes into account the equation that relates the speed of light, which is the c constant, with the wavelength and the frequency. All right, so if I draw this in a little triangle, I can know exactly when I need to multiply and when I need to divide. All right, so I've got c over my lambda term, which is my wavelength, and my frequency, not velocity, frequency. So the speed of light constant is 3.00 times 10 to the 8th meters per second. All right, so it's cycles per second, or a length of time per second. All right, and that's a constant term. Our wavelength, we know that, and our frequency, we also know that. All right, we know those two terms. This one should be in meters. This one should be in hertz. Okay? So I need to know those two things. Okay, an answer or a question will give me one of those each time. And I'll have to solve for the other one. All right, so our question is, a laser CD player. Yeah, how many of you guys know what a CD player is still? A laser CD player uses light with a wavelength of, so it gives me my wavelength. My wavelength is equal to 650 nanometers. All right, so that's going to present a problem there because I'm supposed to be in meters and I'm in nanometers. Okay, but it doesn't present that big of a problem because in order to convert from nanometers to meters, all I have to do is add 10 to the negative 9th to the end of it. All right, so my meters would be 650 times 10 to the negative 9th. All right, that's the negative. Let me clean that up a little bit there. All right, let me try that. Times 10 to the negative 9th. All right, so 650 times 10 to the negative 9th, and it says calculate the frequency. So I'm trying to solve for frequency. Okay, so if I look up at the top here, if I want to solve for frequency, then I've got to divide the speed of light by the wavelength. All right, so frequency equals the speed of light, which is 3.00 times 10 to the 8th meters per second, and I want to divide that by my wavelength, which is 650 times 10 to the negative 9th, and that is in meters. So my meters would cancel out, and I'd be left in seconds minus 1, or hertz. And my answer would be 4.61 times 10 to the negative 14th, I believe. I can't read my writing there for a second, but it's the negative 14th. So that's my answer there. So pretty simple to manipulate that equation there. All I have to do is find my unknown if I know the two of those terms. All right, my second example is taking into account the equation which relates energy to a wave. So a wave has particles. It's got particles in it, and those particles have a certain energy. So more high-powered waves have more energy, and certain waves have less energy. Okay, so E equals hv, and my V represents frequency. So the E term represents energy, which is in joules. Am I spelling that correctly? I think I am. No, that's joules there. All right, so it's in joules, which is represented by uppercase J. My H term is Planck's constant. Okay, by a term from a guy that did a lot of work with energy and waves and how electrons traveled and how much energy it took to move an electron from one place to another. So Planck's constant, that is a term that is constant, and it is 6.626 times 10 to the negative 34th. All right, and that is in joules times seconds. All right, and we all know our V term, our frequency, is in hertz. All right, So our question asks us, the frequency at which an electron travels is, so it tells me a frequency. Frequency is equal to, it tells me that it's 1.15 times 10 to the 14th hertz, which is what the units I'm supposed to be in, and it says calculate the energy associated with the wave. All right, so I can plug that into, I know energy is equal to HV. Okay, so I want to find my energy, and it's in joules, so I need to solve for E, so I do H times my frequency. So 6.626 times 10 to the negative 34th joules per second. And multiply that by my frequency, which is 1.15 times 10 to the 14th hertz. And remember, hertz is the same thing as seconds minus 1, so those seconds would cancel out. And when I do that, multiply those two numbers together, I get the term 7.62 times 10 to the negative 20th. Now we're going to do some more work with these equations tomorrow in class, and we'll look at manipulating them some more.